I'd like to show you our depressurization tool that we have in ProMax. This tool is going to allow us to size like a blowdown orifice for our different depressurization cases. And so I'm going to show you a couple cases and show you how this tool works. So to begin with, we have here a stream, and this stream represents our vessel content, so the material and the composition within some sort of vessel, whether that's a separator, a column, or a pipeline. If I open up the stream, we'll see that our standard operating conditions are 100 degrees and 560 psig, and we have our composition in place, again the composition within our vessel. Now to explain this scenario or this case, our vessel has a maximum allowable working pressure of 625 psig, and we have a rupture disc in place that's set to burst at 10% overpressure. So 10% above our maximum allowable working pressure would be 687.5 psig, and so that's going to be our relief pressure. And we want to know what size orifice we would need in order to get down to our target pressure, which is set to be half of our relief pressure, within a specified amount of time. And so that's what this depressurization tool is going to do for us. Before I actually drag out the tool, an important thing that comes into play here is, along with the relief pressure, which we calculated is just 10% above our maximum allowable working pressure, we'll also need to know what the relief temperature is at those relief conditions, and so that the stencil can start from there. So to do this calculation, I'm going to make a copy of my stream number 1 here. Okay, I've just got a copy here. If I open it up, it starts out, looks exactly the same as our stream 1. But now, instead of being here at my operating conditions, I want to be up at my relief pressure, and I want ProMax to calculate what my temperature would be at that relief pressure. So the key to doing this calculation is realizing that as our vessel pressurizes, as the pressure goes up, the mass density is going to stay the same, meaning we have the same amount of mass within our vessel. And so as that pressure changes, the mass density will not change. And so what I'm going to do is I'm going to copy this mass density, so I just click Control-C. I'm going to delete the temperature because we won't be at 100 degrees anymore. And I'm going to change this to my relief pressure, which is 687.5 psig. And now I'm going to paste back in that same density that I had before. Okay, when I paste that back in, I'm now saying that the contents hasn't changed, the same amount of mass and the same volume, and so at this higher pressure we can expect this higher temperature of 138.8 degrees. Okay, so that's the first step in all of this, is determining your relief temperature at your relief pressure. So with this temperature and pressure, I can go ahead now and actually use my depressurization tool. That tool is found here in our ProMax property stencils. Near the bottom of the list, you'll see one called Depressurization Example. So I'm going to drag that out and place it on my flow sheet. It's first going to ask me what stream or what block I'm looking at. I'm going to choose stream number 2 since it's actually at my relief conditions. And when I click OK, it'll bring up this window with the different properties that I'm going to need to put in to perform this depressurization calculations. So the very first thing you'll see here is our object, which is stream 2. Below that, we can tell it what property we would like to calculate. As I mentioned, there are different cases, different scenarios that you may want to use this tool for. In this case, we want to size an orifice. And so the calculated property is our orifice diameter, so I'll leave that as it is. If you know the orifice and you just want to know how much time it will take to get down to a particular pressure, you could use this time to reach target pressure. Similarly, if you know or have a certain amount of time that you want to use this for, and you know the orifice size, so you just want to know what the pressure will be after a given time, that's another case you could do. There are also cases where you want to maintain the pressure at a particular level, or cases where you would want to keep the temperature at a particular level. And I'll illustrate one of those 2 examples here in just a minute. But again, for now, we want to actually size the orifice or know what orifice size we need, so I'll leave that as is. our venting phase is of vapor, and so if you did have liquid venting, you could choose those options, but we are venting a vapor here. The first thing that it's going to ask us for is what our vessel volume is, and if you can do this depressurization tool on an actual separator or a column, and if ProMax knows the overall volume, it can automatically plug this number in for you. But if we're just doing it on a stream like this, I'm going to need to type in my vessel volume. So this one is 400 feet cubed. The initial pressure and initial temperature need to be my relief temperature and pressure. And if I don't type anything in here, ProMax by default will use the temperature and pressure within my streams. So since my streams are already set up at that relief pressure and temperature, I don't need to type anything in here. But you could type in a number if you like. Similarly, the initial liquid volume fraction. If I know the fraction and want to type that in, I can. If I don't type anything in, ProMax will just look at that stream, look at what percentage of it is liquid, and it will use that number. So I'll leave that blank here as well. The pipe inner diameter, a 2-inch default is what we can use here, but you can again change that. The vent pressure I'm going to keep as atmospheric pressure, but if you did have some back pressure, you'd want to type that in as your venting pressure. The target pressure here is the pressure that we want to get down to, and so we want to cut our pressure in half, get down to 344, and I should be careful with my units, that's in PSIG. The target time is the amount of time we want it to take to get down to that pressure, and so I'm going to leave that at 900 seconds, which is 15 minutes. And from there, you'll see it's going to calculate our orifice diameter, and so this spot is grayed out. We can't type anything in because that's what ProMax is going to calculate for us. Next up, we can tell ProMax some information about our vessel. We can tell it the mass of our vessel and the CP, or the heat capacity of our vessel. What this will do is this will account for the fact that it takes the heat a little bit of time to get through the vessel and to actually get to your contents. Leaving the mass of the vessel as 0 is going to mean that the heat goes directly into the contents, and so it's going to heat up faster. Generally a more conservative approach to things, but if you do want to put in the mass of your vessel, that is fine. But I'm going to leave this as 0 in our case. Next up, we need to tell it something about the heat that's being input into our system. If you know an actual heat input value, you can just type that in right here. But in many cases, if you're doing these fire cases based on API 521, you're going to want to select this option right here. When I have that selected, I'm going to need to give it some of the parameters that this API 521 standard asks for. So I'll need to tell it what my tank shape is. You'll see a few different options here, and for my case I'm going to say this is a horizontal cylinder. We can tell it whether firefighting is available or not, and in this case it is. We can tell it what our tank surroundings are, and those are your options there, but I'll leave this as bare surroundings. Next up, we can tell it what the elevation is above grade, and I'll say 2 feet in this case, and then the length to radius ratio, which is going to be 8. Okay, we also have something called an unwetted area factor. That's going to have to do with how much of the area is not wet, so you're part liquid, part vapor. It's not going to be 100% wet in those cases. The next thing it will ask me is if I want to use an equation of state for the liquid phase. So in this case it's a simple hydrocarbon system, so I'm already using an equation of state. I'm using Ping-Robinson. But if you had a case where you had to use a different type of property package for the liquid, so if you were looking at an amine system or caustic treating or something where you had to use an electrolytic type environment or some other type of environment for your liquid phase, that can really slow down the calculations, although it will be more accurate that way, of course. But in order to speed things up to get to a solution, if you are using a different liquid phase package, you may want to check this box, and that'll speed things up as it makes these simplified assumptions. The last thing to do is to choose our recording interval, so I'll take points at every 10 seconds and that will work just fine. So with all that information, I can go ahead and click solve. You'll see down in my message log that it's beginning to to calculate, and this will take just a minute. But ultimately it's going to calculate what my orifice size needs to be, and it's going to give me some time-dependent properties. And so that's what we have seen on the graphs, and I'll get back to those as soon as this finishes solving. But it's going to show us how the temperature changes over time, how our pressure in our vessel changes over time, and how the mass flow actually leaving our orifice is also changing over time. So let's give this just a minute longer. You'll see that it's iterating on the orifice size, but it shouldn't take too long. Okay, great. We can see that now it's come to a solution. That solution is displayed here on our page, saying we need an orifice diameter of 0.5237 inches. And so that would be the size required. There's some additional information given to us. If I come to my results tab here, you'll see that it has that target pressure and target time that I had input. It again displays the orifice diameter, and then another very important property is the maximum amount of mass lost through this orifice. And so this would be the maximum flow rate through that orifice, and it would be the number that would then be used for the additional calculations after this step. This also tells me how much mass is remaining in my vessel and how much mass total was vented. Okay, and so those are some useful properties. These other properties apply to different cases, and I'll show you that in the second case we look at. But if we come here to the time curves, we'll see these time plots again that were already shown on our flow sheet. But this is just plotting our temperature change, pressure change, and mass loss curves versus time. And so you can copy and paste this data into Excel and then make graphs from it, which is where these graphs came from. But all that information is displayed for you there. On the Compositions tab, it tells us what the composition is of what's remaining in our vessel, and also shows us what the mass is of the material that vented out of our vessel. So all that information is there for you. The last tab here is a Warnings tab, so it's always good to check for our warnings. It will let us know if maybe we've chosen values that fall outside of correlations, or if there was an error in the calculations. That would be where you would want to check for that. Okay, so that overall is our depressurization stencil for this case, and you can see that it's calculated for us how our pressure changed down to our desired target pressure. You can see that our temperature increased over that time, and our mass flow rate did decrease when that maximum flow rate was reported for us. So all this information can then be used. Let me show you one other case here on my second page, and so this is a different scenario, different composition and things. In this case, we're operating at 300 psig and 80 degrees Fahrenheit. Our set pressure for our vessel is 334 psig, and we're using our 21% overpressure for a fire case. And that would mean that our relief pressure is actually at 404 psig. So what we'd like to determine in this case is the required relief valve size that would maintain our vessel at this relief pressure. Okay, so for a certain amount of time we want this valve to maintain our pressure, and so it doesn't keep increasing beyond this 21% overpressure. And so that is another type of calculation we can do here. If I come up here, you'll see this unsolved is actually my stencil's already been put together. I'll go ahead and click solve so that can start solving while we're looking at it. But in this case we've chosen a pressure relief with time limit. And so this again is going to be maintaining our pressure for a designated amount of time. Again, I've typed in my vessel volume. In this case, our initial pressure and temperature are our operating conditions, because we want to know how long it's going to take to get up to that relief pressure, and then we're going to maintain it at that pressure for our designated amount of time. An initial liquid volume fraction has been typed in this case, so again, that's something that the default is given, but you can also override. Our vent pressure is again to the atmosphere with our target pressure in this case. We have a different type of vessel setup and no firefighting. So again, these are all just different options that you can fill out and choose. But you'll see the results, and I'll go to the results tab to take a look at those as well. And what we're calculating in this case is again a maximum flow rate through our orifice, how much mass will be remaining compared to how much was vented. We've got our maximum orifice area, and so that's the number we're looking for, and it will tell us what the temperature and pressure is at that case, and what our maximum, or what our flow rate is at that maximum orifice size. Our time curves are once again available for us. We see in this case, as the pressure builds up, we start without releasing any flow, and so we're zero flow until we get up to the relief pressure. If I look at the composition, once again we have the composition remaining and the composition vented, and it tells us the composition vented right at that max orifice size. And so that's a look at another type of case that we can do with our depressurization stencil. A very useful tool, and so I do hope that the tool is useful for you, that this video helps you understand how it's used. And as always, if you ever have any questions or any concerns, feel free to give us a call. Our number is 979-776-5220, or you can email us at support@bre.com. So thank you for watching.